Morning. So, been watching some videos about people's understanding of the universe, and I have this theory which I think I've mentioned before, but just for the fun of it, I'm gonna mention it again. Also, I might get a phone call relatively soon, so if I do, I'll have to quit in a rush. But if the universe is contracting instead of expanding, wouldn't we theoretically see the singularity that it's contracting towards? So, also, if the universe is expanding like it is, but the mass of the universe is mostly outside of the cosmic event horizon, wouldn't we also see a center point of like infinitely fast expanding universe, like a 0 point field expanding from a center point outward, which would be basically every point outward. So if the universe is expanding fast enough, wouldn't we see a strange glow of light that will eventually become overpowering? And if the universe is contracting, I find it reasonable to think that we would see a single center singularity. I think, though I'm not sure. Nipple. Moving on.
Refreshing beard and face wash from King C. Gillette. Master your style.
Fact. In a black hole, all of the mass is concentrated at the singularity at the very center.
Perhaps.
Fact. Every black hole singularity is surrounded by an event horizon. Nothing can escape from within the event horizon unless it can travel faster than light. Fact. Gravity travels at the speed of light. So how does a black hole manage to communicate its gravitational force to the outside universe? How does gravity escape a black hole? In 1915, Einstein presented to the world the equations behind his general theory of relativity, which described gravity not as a traditional force, but rather in terms of the curvature of the fabric of space and time. Einstein's theory predicted the existence of the ultimate gravitational object, the black hole. These are objects of such extreme density that the fabric of space is dragged inwards at greater than the speed of light. According to Einstein's theory, any object that reaches such a density has to collapse to a point-like singularity of infinite density surrounded by this boundary of no return, the event horizon. General relativity made many other predictions. One of them is that gravity itself has a speed. Einstein built the equations of GR so that they would be consistent with his special theory of relativity, which describes how lengths and times and other properties depend on how fast you are moving relative to the speed of light. Special relativity enshrined the speed of light as the absolute cosmic speed limit. It tells us that light speed is the maximum speed at which any causal influence can travel. It's the maximum speed of information, the speed of causality. Naturally enough, the c of the speed of light made its way into the equations of general relativity. When you use those equations to calculate the speed of various gravitational effects, they also turn out to be the speed of light. For example, we have gravitational waves, ripples in spacetime caused by certain types of motion. They travel at the speed of light, and that's been confirmed when gravitational waves from colliding neutron stars reach us at about the same time as the corresponding electromagnetic radiation from the explosion. But this speed of gravity also tells us how quickly a regular gravitational field changes. Imagine for a moment that the sun just disappeared. Now, you can't just erase mass, but let's pretend that you can for the sake of argument. It would take 8 minutes for us to notice the sudden darkness, and the Earth would continue to orbit the now empty patch of space for the same time. It would take 8 minutes for the sun's deep indentation in the fabric of space to smooth itself in the wake of some pretty crazy gravitational waves. But here we have a problem. If gravity travels at the speed of light, and all the mass of a black hole is hidden beneath the event horizon, how does its gravity get out to influence the surrounding universe? Shouldn't a black hole's event horizon protect the universe from its own malicious influence? To answer this, we're going to look at gravity in two completely different ways. First, we'll see what Einstein has to say on the matter, and then we'll go deeper into the speculative realm of quantum gravity. Starting with good old-fashioned general relativity. There's no question here, a black hole's gravity doesn't care about the event horizon at all. In GR, the gravitational field, the curvature of space-time, has an independent existence to the mass that causes it. For example, when Earth feels the pull of the sun's gravity, it's not directly interacting with the sun itself, it's interacting only with the local part of the gravitational field. Same for a black hole. The space around the black hole doesn't need to know about the mass of the central singularity. It only needs to know what the space next to it is doing. There's this old analogy of space as a sheet of rubber stretched by a heavy mass. It's not that great an analogy in many ways, but here it's actually useful. The rubber at any one point in the sheet doesn't know about the massive object. It's being stretched only by the pull of neighboring patches of rubber. And there's another way to think about the action of gravity. Instead of stretching space-time, we can think about space as flowing towards the massive object. The speed of space is just the speed of a free-falling or inertial observer. Fallen from far away, an observer and the patch of space that they occupy reach light speed at the event horizon of the black hole. A close analogy to this picture of gravity is a river flowing towards a waterfall. The water is the fabric of space, and it accelerates towards the drop. At some point, it exceeds the swimming speed of any possible fish. That's the event horizon. Any fish that passes that point will be carried to the singularity, the fall itself. But let's think about what pulls any patch of water. The water at the event horizon doesn't know about the fall. It's pulled along by the water a little ahead of it, which in turn is pulled by the next adjacent patch, and so on. Gravity works like the rubber sheet or the flowing river. One patch of space doesn't need to see the ultimate source of the field. It only needs to see the next patch along. Depending on how you think about it, the curvature or the motion of each patch influences the next. This explanation works for the black holes of general relativity, but we know that GR is not the final theory. It breaks down at very small distances and in very high gravitational fields, for example, at the black hole singularity. Many physicists believe that general relativity needs to be replaced by a theory of quantum gravity to explain the behavior of gravity in these circumstances. So, can gravity escape from a real black hole of quantum gravity? Now, in quantum mechanics, or more specifically quantum field theory, forces are mediated by particles, not by the geometry of spacetime. For example, the electromagnetic force is communicated between charged particles by transferring virtual photons, ephemeral excitations in the electromagnetic field. In theories of quantum gravity, the gravitational force should probably also have a mediating particle, usually called the graviton. Okay, fine, but doesn't that make things worse for black holes? If gravity really is communicated by a particle, how does that particle escape the event horizon? Well, actually, even in this picture, the event horizon has no way to halt the force of gravity. There's a bit of a misconception in how we think about virtual particles. They don't really travel from one location to another, carrying force with them. Virtual particles aren't localized like that. Let's say two electrons approach each other. They interact by exchanging a virtual photon, or more precisely, they exchange the sum of all possible virtual photons. But those photons don't follow a well-defined path between the interacting particles. They sort of emerge from the electromagnetic field in the broader region occupied by both of the electrons. And their some defect leads to a repulsive force between the particles. So if gravity is really mediated by virtual gravitons, then those gravitons don't emerge from the location of the singularity. and they don't have to travel through the event horizon to do their work. The gravitational field around the black hole is already abuzz with virtual gravitons. Now, you might ask why those gravitons themselves don't get swallowed by the black hole. Well, that's easy. These are virtual particles, and in quantum field theory, virtual particles are not restricted by the speed of light. They can travel at any speed. Interactions between particles result from the sum of all virtual particle interactions, possible and impossible. And the speed of light limit actually emerges in a sort of statistical way. The overall interaction, along with any information that it communicates, has to be sublight speed. But if we're describing the gravitational field as being built up by virtual gravitons, then the event horizon is no barrier at all. Unfortunately, you still can't send an SOS message from inside of a black hole that way. And this idea of sending information across an event horizon brings us to our last argument. And this one works whether we're talking about the classical gravity of Einstein or some deeper theory of quantum gravity. The cosmic speed limit is the speed limit of information. To experience the gravitational effect of a massive object, the information about the presence of that mass does have to be able to reach you. We have to be able to see that mass, at least in principle. And it might surprise you to learn that you actually can see the mass of a black hole. The present mass of a black hole is hidden below the event horizon, but we can see its past mass. And it's the gravitational effect of that past mass that we actually feel. Think about a star collapsing into a black hole. As it approaches the surface that is to become the event horizon, it approaches light speed with respect to someone watching from a distance. According to relativity, that means its clock slows. It appears to freeze at the event horizon, and the light it emits becomes stretched out and sapped of energy. The star does appear to go black, but really, the faintest signals of that collapsing star continue to make their way out into the universe over infinite time. That's ignoring the whole Hawking radiation, black hole evaporation thing. So we can still see the mass of a black hole. It's imprinted on the event horizon. Whether gravity is communicated by the curvature of space-time or by virtual gravitons, we maintain a causal connection to the mass that generated that gravitational field. And for those of you who love their Penrose diagrams, just think about the source of the gravitational field as always being in your past light cone, and that has to be outside the black hole. And this last argument also tells us how it can be that a black hole can possess electric charge. If a black hole swallows electric charge, the electromagnetic field around the black hole grows. How? Because when you look at a charged black hole, you still have causal contact with all of the charge that fell into it. You interact with the past charge, not the present. From the point of view of that charge, it is inside the black hole, but from your point of view, it's now frozen on the event horizon, but is happily exerting its influence on the surrounding universe. This whole question is related to another very interesting one. In a black hole, where is the mass? A simplistic view says that it's at the singularity, but that's not the mass you interact with. You interact with the local curvature of space-time, which is produced by the past mass, which from your point of view is on the event horizon. In fact, the whole idea of mass is poorly defined in general relativity, in part because the gravitational field itself has energy and so is a source of mass. To get a consistent definition for mass, you need to integrate, add up the contributions to infinite distance from the black hole. By that definition, the mass of a black hole is everywhere, so it's not surprising that it can escape the horizon. To sum up, don't mess around near black holes hoping that the event horizon will protect you from the black hole's gravity. Many seemingly different pictures all point to the same result. The black hole will eat you right up. And even as you're getting crushed into an infinitesimal point, you can rest assured that your own mass will continue to exert its gravitational influence on exterior regions of space-time. Before getting to comments, we'd like to thank our supporters on Patreon. And today's special shout-out goes to Alex Kern,
Are you here to heal the world?
On average, our hearts beat 1.3 times. They pump 6.3 liters of blood around the body. 4 babies are born worldwide, and 2 people die. To a human, a single second is not a very long time. And yet, in the entire universe, our planet travels 220 kilometers in orbit around the center of the galaxy. Our sun loses about 1 million tons of its mass out into space. 4,800 new stars are born in the Milky Way, and across the observable cosmos, just under 1,000 supernovae blow entire star systems to smithereens. A lot can happen in 1 second. But is it enough time to build a universe? The smallest fraction of time by which we measure our lives, the second can trace its origins through thousands of years of human history. As early as the 23rd century BC, the ancient Sumerian and Babylonian civilizations devised a system of counting based on the supremely divisible number 60. Later, the Egyptians favored the practicality of the number 12 as the number of finger joints on a single hand that could be counted with the thumb. Our modern concept of time is thus built upon these cultural preferences. Atomic clocks, the universal standard for measuring time on Earth and in space, define a second as 9,192,631,770 radiation pulses of an irradiated cesium-133 atom. As an ultimate definition, it is accurate, precise, but inelegant. It is a reflection of our history, our perception of time, space, and matter. But 1 second seems impractical when considering the history of the cosmos as a whole. Indeed, on a cosmic scale, our universe has clocked up some 436 quadrillion seconds so far. And those seconds can also contain almost incomprehensible vastness. In 2020, scientists in the German electron synchrotron in Hamburg bombarded hydrogen atoms with X-rays, knocking electrons free from their orbits and sending them skipping to the adjoining atom. As the speed of light is the fastest you can go, and hydrogen is the smallest molecule there is, the time it took for this to happen was and is the shortest fraction of time ever measured in an experiment. That time was 247 zeptoseconds, or nearly 250 billionths of a trillionth of a second. There are 2,500 times more zeptoseconds in a single second than there have been seconds in the history of the universe. And so, as we peer back through the eons, glimpsing the universe's childhood from distant and ancient starlight and reconstructing its growing pains in powerful particle accelerators, we uncover a surprising truth. 1 second is more than enough time to build a universe. For most of its existence, our cosmos has looked surprisingly like it does today. Stars have lived and died, galaxies have formed, spun, and collided. Space has calmly expanded and cooled. But our universe did have a beginning, a period of wild revolutionary change, assembling an orderly cosmos from practically nothing at all. Though a single second seems barely long enough to accomplish the ultimate act of creation, as we shall see, the briefest of moments to our human eyes can be an eternity from a different perspective. And incredibly, we can draw a clear line back from our vast present cosmos to the miraculously perfect mix of raw ingredients that came into being in that first moment. So, just how recognizable is our universe when just a single second has passed? Is the cosmos we see and feel around us already inevitable? And with 436 quadrillion seconds to choose from across 13.8 billion years, could it really all come down to the first one? Across the Earth, a cyber attack happens once every 39 seconds, which is once every 39 trillion billion zeptoseconds, or 2,200 times a day. NordVPN has been kind enough to sponsor this video, and they are a premium.
Mäkkäristä saat aina
Could go
enemmän
from
pikkurahalla.
McDonald's.
I remember some of the first questions. I would ask my teachers back in the days when I looked at the night skies and saw darkness. And obviously, many of us do have the same questions. Why is the night skies black? Why do we have so much darkness out there and so few stars in between? Hello, wonderful person. This is Anton, and today we're going to be talking about some of the new discoveries in regards to a concept known as extragalactic background light, EBL for short. The light that's present if you were to remove pretty much all of the galaxies and all of the stars, the light that technically represents that darkness I wanted to know more about. And interestingly enough, the recent findings from one of the teams suggest something we didn't really understand about the light. When studying this light using some of the new observations, the scientists discovered that everything seems to be just a little bit brighter than we expected. As a matter of fact, at least twice as bright as the theoretical predictions based on the number of galaxies we know of in the universe. And at the moment, it's somewhat difficult to explain. But let's talk about these concepts in a little bit more detail because it does actually involve several ideas that are often misinterpreted or often misunderstood. So first of all, we have what's known as DEBRA, diffuse extragalactic background radiation, with the brightest member of DEBRA being so-called cosmic microwave background or CMB. But this is obviously only visible in the microwave frequency and doesn't represent other background radiation that can be detected in other frequencies as well. And so in theory, if you were to look at the night skies with some kind of a very powerful telescope and to then start removing pretty much everything we see here, so basically removing all of the bright stars, removing all of the galaxies that might be also extremely bright as well, and possibly all of the other sources of light known to us, you're going to be left with EBL, extragalactic background light. Light produced by a lot of other things we still don't really understand, but for the most part, believed to be produced by various extremely distant and relatively powerful galaxies. Specifically, a lot of really early galaxies existing at the beginning of the universe, with many of them producing a lot of stars extremely quickly, so-called starburst galaxies, and also galaxies producing very powerful jets such as quasars and blazars. But the thing is, seeing this from planet Earth is extremely difficult, and it's difficult for several reasons. And one of these reasons is sort of visible in this video right here. There's actually quite a lot of glow in the night skies produced by various dust in the solar system, but also in our own galaxy, with some of the brightest glow mostly being from the so-called zodiacal light. The light you see produced right here, that's actually hundreds of times brighter than the background light we're trying to detect. Now this right here has a very interesting origin, and there is a video about this from a relatively recent study that suggests that the zodiacal light is actually maybe produced by the dust from Mars. You can check out this video somewhere right there or in the description below. With the other type of light, such as galactic light, which is usually produced by dust located in the galaxy itself, also preventing us from seeing certain regions. But this type of light we can avoid by, I guess, looking in the opposite direction. But how do you avoid the zodiacal light that's produced by possibly Mars? Well, in this case, if we were to somehow find a way to look at the night skies really far away from planet Earth, from planet Mars, or somewhere on the outskirts of the solar system, we might be able to see this extragalactic light we're trying to see. So naturally, here the scientists decided to use the iconic New Horizons mission. The iconic probe that visited Pluto back in 2015 took some incredible photos of Pluto and discovered quite a lot of things about it, and that's currently on the way out of the solar system and is going to be moving into the darker areas. And so in this case, by using the New Horizons probe and by looking in the regions of space where there is not much going on, so basically by looking at complete darkness, it might become possible to, first of all, calculate the total amount of this EBL, but to also possibly see something we've never seen before. And one such discovery was already made by the probe a few years ago. You can find the video for this in the description below as well. But in this case, by just looking at the optical light of EBL, the so-called cosmic optical background, the scientists realized that, well, it seems to be at least twice as bright, suggesting, of course, several different things. Now, one of the more obvious explanations here is maybe in regards to this just being an error. So, for example, maybe the New Horizons probe is actually producing it itself. Specifically, maybe the instrument used here, known as LORRI, may be somehow producing additional foreground light. And even though it was suggested previously that the nuclear power source present in the probe could maybe somehow be responsible for the light produced here, in this study the scientists have already taken it into consideration, so they don't think it's coming from the probe itself. But if not the instrument and if not an error, what could it be? Well, just like the previous explanation from a few years ago, in theory, this could be a representation of a lot of different galaxies we just didn't know existed. There could be a large population of relatively difficult to see galaxies that could be just below the detection limit for other telescopes. If this is so, there's at least one telescope that's going to be able to resolve this issue. James Webb Telescope, in theory, should be able to find these ancient distant galaxies. The other explanation involves potential existence of tremendous numbers of so-called rogue stars. Stars stuck between galaxies in the intergalactic space that might have gotten kicked out by various galactic collisions and whose numbers we might have underestimated. Once again, potentially a job for James Webb Telescope to resolve, with some other more exotic explanations involving things like Cherenkov radiation from gamma rays, the type of radiation we usually see in, for example, a typical nuclear power plant, or maybe different types of light reflected from the galactic dust present in the Milky Way. In other words, currently nobody really knows what's going on here, but the results seem to be confirmed from previous studies. In other words, there seems to be a little bit more light than we expect from the background light of the universe. The universe seems to be just a little bit brighter than we expected. Or to answer my own question from early childhood, the universe doesn't seem to be dark after all. But unfortunately, it will probably take us a few years to answer these questions. It will take a lot of observations from James Webb Telescope, and it will also take projects like this one known as Sphere X, or this one known as Cyber and Cyber 2, to help us answer these questions and to actually help us determine the exact values for all this cosmic microwave radiation and extragalactic background light. And so, at least for now, this has to stay as a mystery. The universe is brighter for reasons we cannot explain. But whatever the answer is, it's probably going to be really exciting. So make sure to subscribe because we're definitely coming back and talking about this in some of the future videos. Until then, thank you for watching, subscribe, maybe share this with someone who loves learning about space and sciences, and maybe come back tomorrow to learn something else. Support the channel on Patreon by joining channel membership or by buying the wonderful person t-shirt you can find in the description. Stay wonderful, I'll see you tomorrow, and as always, bye-bye.
Interesting. The universe is twice as great as we thought it was. Posted my 25,000 AD storyline here. Looking for any reactions that it gets, and I've already gotten one like. Hope I get more. I'm not sure if you can see it there, but the reason I'm on the floor is because the bed actually broke. There was a bedpost or bed leg that actually broke. So, this has been an interesting broadcast. To be succinct about it, I believe if the universe were to be contracting instead of expanding, that we would see a bright ball of light in the night sky that is not the sun. But that is my opinion. So, that is all. Thank you for watching.